welcome to Module 37 on overfitting capacity and deep network generalization. So by the end of this module, you should be able to explain the concepts of capacity, overfitting, underfitting, and generalization, a lot of which we've already seen, but more specifically in the context of deep neural networks, which I mentioned is going to be the primary subject of the remainder of this course. You're going to be able to relate training versus validation, test behavior to those kinds of phenomena. And we're going to introduce the idea of a generalization gap, which we kind of made implicit earlier. You'll be able to diagnose capacity-related failure modes in deep networks using learning curves and simple experiments, compare different ways of controlling effective capacity. This includes architecture changes, regularization, different uses of data, different uses of training time. And you'll be able to justify model and regularization choices in a deep learning setting using evidence you provide through experimentation. So earlier in the course, we've seen bias variance trade-offs and learning curves. We've introduced regularization of a few different forms, L1 and L2 being primary among them. I don't think we used the term weight decay when we talked about L1 and L2 initially, but either today or in the next module, we're going to talk about weight decay kind of broadly in L1 and L2, given that they kind of reduce the size, the absolute magnitude of these weights is a form of weight decay. We've also talked about hyperparameter tuning as a form of regularization. And then we've also seen optimization basics. We have a whole module on optimization, and we've seen aspects of it through various other modules. But now, we're dealing more and more with relatively deep neural networks. So we have to sort of be more accustomed to the effects of deep learning on these factors. Deep networks, to some extent, can be very powerful, but they can also be a little bit temperamental. I think I described them as you have to approach them slowly from the side and use a soft voice when you interact with them. That's a joke. The large networks can, so these large neural networks can memorize things, but they can also still generalize, which is a bit of a paradox according to our previous conceptions. We might see a little bit of this later. But previously we said, well, if networks are memorizing or overfitting too much to the training data, then that means that they will fail to generalize. So validation will be poor if they're overfitting, while training losses can be very low or training performance can be very good. But here it's sort of like both of these things. You have memorization and you have good generalization. And so the problems can be a bit more subtle. We're going to look at learning curves again for deep learning models. Again, things are going to be subtle, so we have to be careful not to fool ourselves in how we interpret them. And we're going to start making connections, as always, to future topics. Dropout and batch norm are going to be the topics of the very subsequent module after this one. And then thereafter, we get into representation learning, transformers. So some of these concepts will come up today. So conceptual scaffolding. This is sort of the classical view. I think we had this very same graph in a previous module. As you increase the capacity of the model, either with more depth or more width or more parameters generally, more flexibility, then the idea would be that you generally get better and better fitting. So the training error would go from underfitting, so like too few parameters, too little capacity, means you can't represent the complexity of the data. But as you increase the capacity of the model, you get better and better performance on training data. And for a while, you get better performance on validation data, like generalization works pretty well. But at some point, you start overfitting to the training data, you end up getting this high variance problem, and you don't want that. The whole name of the game is generalization. So really what you want is kind of a sweet spot, someplace down here where the validation error is lowest, even if the training error isn't. That's what we're kind of looking for. This is obviously a cartoon example, even for classical models, but this generally was a behavior that held pretty well, as we've seen in previous modules. So you already know this. If you have low capacity, underfitting, high or very high capacity is overfitting. How this relates to bias and variance is a topic we've returned to several times. And what we want is like the best of both worlds, a balance, like so many things in life, to achieve the sort of sweet spot that we're looking for. Now the problem here, or the complexity anyways, is that deep networks can be so over-parameterized that there's more parameters than data. and that they can still generalize. So this kind of like seemingly paradoxical effect was described in this iClear paper, for example, but in other places as well. So you can memorize and you can generalize, which is, I guess, a good thing in some point of view, but we'll come back to that in a moment. Optimization, regularization, and the general shape of the data, so to speak, shape the effective capacity. So it's not just like you have one knob you're turning and you decrease or increase the number of parameters you have, and that is the extent of what capacity means. Again, like how you optimize, how you regularize, that has a large effect on your capacity of your model, whatever model it is, and it's exacerbated in deep neural networks. So here we're going to start from our classical conception, which we had for the first third or so of this course generally, and we'll kind of introduce complexities with regards to why deep networks don't always follow that picture. So here's a little anti-example. We have good training accuracy and we have good validation accuracy. So we have 99.9 training accuracy, 99.8 validation accuracy. Everything looks great according to this fictional scenario. And then we take our test accuracy on some slightly shifted data set. So this could be the case, again, in situations where you're working outside of computer science in domains where the test set is like truly held out. In fact, this is even true in computer science. There's a lot of workshops where there's a competition, and the organizers of the competition just don't show you any of the testing data. You send them your models, and you send them your scripts, and then they run your code on their data. So, or in the case of say healthcare, you have tons of data at your site, and then you deploy it to a hospital up the street from your site, and performance doesn't seem as good as it ought to. So this is a bit of a problem, right? Like we were trained, at least in the first several modules of this class, that if you have good validation accuracy, then validation is a proxy for generalization. It's a proxy for the test set, and we really shouldn't have this kind of dichotomy between validation and accuracy, test performance. So, I mean, the idea here is that there's some distributional shift. So you're using different hospitals, different devices, different demographics. The slight differences that kind of shift all of the data. So the model has actually overfit to the training distribution. The training distribution happened to be very close to validation data distribution, whatever data we happen to have. And it's still not generalizing well. It generalizes well within your body of data, but not elsewhere. I guess the story could be like you're training your data on, you're training your model on data gathered from one social media platform. You have a ton of data from them, and you do the right thing, and you do held out data for testing, and you have validation sets and everything. But when you shift to another platform where the population just behaves differently, then you're gonna have a bad time. So here the main takeaway is actually this kind of notion that validation being the gold standard for generalization, this is not going to be true. You're going to need to think about how data were collected, what kinds of shifts might occur in the real world after you've deployed your data, like beyond the data you actually have. So how do you evaluate your design? Are you literally just looking at accuracy? Should you maybe be looking at other statistics in order to predict this kind of massive drop-off? And yeah, like what kind of again, try to break the system. I mentioned this in class several times. I think I mentioned it in some of these videos, that what you should be doing is try to break the system. I don't want to go on too much of a rant, but in the movie 2001, A Space Odyssey, one of the first and best movies about AI, the humans were trying to evaluate whether or not there was a problem with their onboard AI computer called HAL, and they did that by basically just shifting things, trying to trick it, trying to break it, figure out what goes wrong. I mean, for them it ended worse than it might for you, but the point is, the best way to understand a system is to understand how it breaks. You should really watch 2001: A Space Odyssey, by the way. So yeah, there's risks on recall. So let's use a simple classification or regression setup. This is going to be true for either condition. You still have your supervised data sets. These data are sampled IID from some unknown distribution P, the universal distribution P. And again, we have a model f of x with parameters theta. We again have our population risk. This is like the true risk in the world. Like we we don't actually have this, but we know that there's some loss function that compares our predictions to real observations, which can nevertheless be noisy. And these data, X's and Y's, are just sampled from this universal population, which we don't have access to, and we have an expectation over that population we don't have access to. So this is very theoretical. But like we talked about in the very first week of this class, we can mimic this population risk using the empirical risk. The empirical risk has a certain amount of training data, n, and we just sum over all of the losses for the training data we have, or for the data we have, and then we normalize, we divide by n to get the average, and this is our empirical risk on the training data. So we know this we know how to conceive of empirical risk in the classical view of machine learning. So this is a minor thing. Again, this is kind of implicit before, but we have this idea of the generalization gap. The generalization gap is the difference between the real population risk, which we defined a moment ago, which we don't necessarily have access to, and the empirical risk, which we can compute empirically on our available data. Oh, mistake. This is a LaTeX bug here. This is theta. So in practice, you can estimate this population risk using the validation set, or maybe even the test set. So I don't have access to the universal background model of risk, but I can estimate it by this generalization risk according to the validation set. Already, we're maybe straining against a little bit of incredulity here, because wait a second, this theoretical population risk is over the entire population, which would be a massive amount of data, and here we are estimating it with a data set that is even smaller than the training set. There seems to be a bit of a gap in terms of our credulity here, but the main notion here anyways is that our parameters are set according to the training set, and we're still interested to see how things generalize. So we can estimate this generalization gap just by the difference between the validation curve or loss or risk and the training risk. So this is something we've been kind of doing already anyway, just visually in some of our graphs. This just formalizes it very, very simply. Again, I'm going to fix this bug in a second, or this typo. So obviously a small gap, a small difference between validation and training suggests that we ought to have good generalization, assuming that there's, again, the problems of leakage between validation or test and training don't exist. But if there's a large gap, then this is a candidate for suspected overfitting, like we talked about before. If we're talking about, you can also generalize this. So this is about loss and risk, but you can generalize this same concept to the differences in accuracy. Here, we expect the accuracy for a training set to be bigger than the accuracy for a validation set, so we subtract one for the other. I think it's reasonable to also just take the absolute values of these quantities. Here we're moving the terms around in order to get a positive value of this gap. Again, that's a bit of a, at least to my point of view, it's also a little bit of a hack. So you can put absolute values across these things, maybe even square them. We love squaring things in machine learning. Square the difference. That might be a bit of a better way to think about this, but the core idea is the same. This is just one of many ways we can measure the gap between training and potential generalization. So again, we talked about deep neural networks. They have a lot of parameters, and they have so many parameters that what constitutes capacity of these models can also depend on other things as well. Everything becomes very sensitive. So you have number of layers, which can be anywhere from 2. Technically, 2 hidden layers is a deep neural network according to tradition, or hundreds of layers. Units can have a few hundred. Layers can have a few hundred hidden neurons each, or they can have thousands or millions. The kind of connections we make. Residual blocks I've hinted at. We're going to come back to that later in this course. Attention also we've hinted at. We'll come back to that later in this course. So there's various kinds of ways you can also hook things up in more complicated ways than we've seen so far. Whether we're using ReLU or Soft Plus or GALU or GLU, how we approximate nonlinearity or how we estimate nonlinearity can also change capacity, and how we end up having or modulating training dynamics. Of course, more parameters usually means higher capacity, but if you have very strong regularization, or if you have a very kind of limited focused optimization, this can also reduce your effective capacity. you have a potentially very strong model, but you put them in a situation that limits their abilities, like a smart student who's not not doing the exercises. So in deep learning, this is the key idea. Deep learning is not just about the mere parameter count, although those parameter counts can be huge. It's parameter plus all these other things that we're throwing at the training. So let's work some examples and just kind of explore what overfitting means in deep networks, or could potentially mean in deep networks. First, we're going to do a deep regression, and we're going to look at over and underfitting. We're going to start with a simple one-dimensional regression toy problem. It always helps to start there, just for visualization and just to get the idea across, so you can see this visually to some extent. We want to compare small versus large neural networks, and we want to compare how they compare we want to compare them on the same data. So we'll look at training and validation, mean squared error, because this is regression, and we'll just look at the shape of the learned function like we have before. The input will be data drawn on uniformly, and the target will be this little function. So it'll be sine of x plus like a diminished 1/4 sine of 6x, so a bit higher frequency component with a small amount of Gaussian noise. We're not going to talk too much about audio signals here, which is a shame because I really love audio signals, but this kind of function, if you were to have a very long sequence of sine waves, each with different frequencies and different amplitudes, you could technically construct any sound, any voice, any word. Over a small period, over small regions where the signal is invariant to time. Anyways, I'm getting off track here, but this kind of sum of sinusoids is a very common way of representing audio and other signals, even like echocardiograms and so on. So it's very simple, but we're starting to see a little bit of complexity just because this isn't a simple sine wave like we've seen in the past. It's like two sine waves superimposed over each other. This is what it looks like. Not too complicated, really. You can really see the effect of the low frequency, high amplitude sine wave, which is the overall function that you're seeing behind the scenes here. There's also a small little component that is making small changes, adding noise in some sense. We also have actual noise epsilon, which is provided, well, here, down here, on line 9 and 10. Anyway, this is the overall data. The training data and the validation data are sampled from the same distribution. So we're going to use PyTorch. We're going to increasingly use PyTorch to define our neural network models. It's because of how popular PyTorch is in deep learning. We have small multi-layer perceptron with 1 hidden layer with 16 units, and then we're going to have a large MLP with 3 hidden layers, each with 128 units. This is different enough. Going forward, I'm going to introduce these two ideas. This is really engineering more than the theoretical part of this module, but it's worth mentioning. When you're working with PyTorch, you're going to see lines of this, usually at the very beginning of any kind of code. This is very important. As you know, deep neural networks benefit greatly from heavily parallelized processing, which is made available through graphics cards, GPUs. I was going to say, normally it's NVIDIA that provides these cards, as you probably also already know, but and NVIDIA has this library called CUDA, which is used quite a lot in deep learning. Just a quick note that a lot of these integrated chips, in particular AMD, has integrated chips where like the full system memory and the GPU memory are integrated together. Apple does the same thing now. I'm not too sure about Apple, but on AMD there's a platform called ROCm, or ROCm, and you can run CUDA code on AMD hardware. So I'm just trying to put that out there. It's even though NVIDIA is surely a monopoly and something ought to be done, you can still run a lot of great machine learning on AMD hardware, and in fact, like the integrated memory can often have a lot bigger capacity than NVIDIA for similar or even cheaper prices. Anyway, that's a side note. The main thing, since we're talking about devices here, so you have a computer, you have a server somewhere. Usually the server will make it known whether or not the GPU is available. So if torch.cuda.isAvailable is true, then you set the device on which you're doing your machine learning to CUDA, and then all the computations that can be run on the GPU will be sent there. Otherwise, it'll just be run on the CPU, and it'll be a lot slower. So slow, in fact, that sometimes it won't even be feasible. This is very important. If you don't do this line, it's a bit annoying to have to always do it. Why can't it just automatically do this? But it's it's open source, so it's good tell the system what you want it to do. You have to do this, otherwise you're going to not benefit. And then you have to also explicitly send computations to the device. So you have some large neural network that you've implemented. It's part of the Torch framework. In order to actually run it, for training or inference on the device, then you have to just call this line also. So if the device is CUDA, then your neural network is sent to the GPU. If it's not CUDA, it's sent to the CPU, and you're going to be waiting a long time. But these two lines are just a bit of overhead you have to do in order to take advantage of modern GPUs if available. So I just wanted to mention that because I think this is the first time I use these very important lines in code in this class. So here is one of them on line 5, and here I send the neural networks to the device on lines 39 and 40. Otherwise, the construction of these neural networks is nothing that we haven't seen before. We have a sequence of layers. We have linear layers that feed into the ReLU nonlinear activation function, and we have a couple of these one after the other. So there we have it. Anything else to report? Yeah, so this is the one hidden layer for the small one, and with 16 units, and we have 3 which are 128 units each for the large MLP. All I'm doing here is just like describing the number of parameters I have in each. So the small neural network has a mere 49 parameters to learn, and the relatively large one has about 33,500. So here's our little training loop. Again, we've seen this already also, so I'm not going to go into all the detail, but just to mention, we are going to go train over epochs, like we've done many, many times in this class, and we're going to increasingly use batches for efficiency's sake and for generalization's sake. So we're taking batches of X's and Y's and using those batches for training. And again, just speaking of overhead, as I mentioned in a previous module, because we're pushing these gradients back within the neural network and we're kind of accumulating them as we do, we have to remember to zero them out every time we have a new batch, which we do on line 14. This is, again, a bit of overhead that you have to do. If you don't, things get bad. What am I doing at the bottom? I'm just showing the tail of my history of these training processes. So the last few rows of these 200 epochs are shown at the bottom here, and we have the training MSE and we have our validation MSE, which are kind of tracking downwards in each case. And the large neural network seems to be getting much smaller. Training mean squared error and about half the mean squared error in training, and a bit more than half of the mean squared error in validation. So things seem to be better the bigger network we have. And indeed, visually, just visualizing that sequence of epochs we just saw textually, we have the small neural network, which has these smooth curves in training and validation. They track each other. Everything seems okay. They track each other downwards. The gap here you can see between validation and training is basically the distance between the blue and orange curves here. We have the large neural network, which has a much faster decline in mean squared error, which is great, and it gets low fast and it stays low generally. But you might notice right off the bat here we have these spikes that are occurring. This is going to be a very frequent, a very common thing for you to observe when you're doing your own training with large neural networks. Curves are rarely as smooth as we see here for the small neural network. They tend to jump around a lot, especially if you're using batches. So we have these massive spikes in error, despite a general behavior or trend. We can visualize our fits. Just again, we want to interrogate and see what the model is actually learning, to see if it's learning anything useful, to see if its learning dynamics are really going crazy. So here we have our true training data are these blue circles. We have the true sine wave. Actually, over here, I think I failed to plot everything. I should correct this too. So remember, we have 2 components for the sine wave. We have the slow one, we have the big one. So I'm going to go ahead and add this also. Add the extra sine wave before I post the slides. But yeah, you remember how we produce the true data. I mean, to some extent that doesn't matter too much because you have the true data here. But then you can see the behavior. The main story here is the difference between the behavior in the small neural network and the large one. The small one has this kind of smooth orange curve, which is a little bit janky, but generally it's smooth. It's not going crazy. It's not behaving erratically. The green curve is the behavior of the large neural network, and even though it has better performance on training and validation, you can see that it is behaving a little bit unpredictably. It is like jumping around a little bit, somewhat erratically. Why is it smooth below -1 and then starts jumping around, especially between 0 and 2? That's something that we might not know at this point, but it's a little bit surprising, right? So again, like we're trying to compare the small and the large neural network and make a decision about which one to deploy. We might be overly satisfied with the large neural network and just say, well, it gets better validation and training error, and that should suffice. But you might notice that the difference between the curves for validation and training seem to be getting slightly bigger for the large neural network compared to the small neural network. And that might be raising some alarm bells, and also this kind of jankiness might be raising some alarm bells also. So don't just rush into deploying something without thinking about it first. This is our overall model. We're just comparing the number of parameters versus the final validation and training MSEs. So this is true of this particular example, and it's true of a lot of similar examples. Oh, sorry, I don't know how long ago that happened. I noticed my massive face. I'm going to go ahead and see if I can use this. There we are. Large neural networks tend to have much lower error, much lower empirical risk. This might indicate that they have a higher capacity, or at least it's correlated with their high capacity. In this run, it also achieved lower validation, empirical risk, mean squared error. So the extra capacity might have actually helped its generalization here. But I want you to go ahead and do some experiments, fiddle with increasing or decreasing your parameters for your large neural network, and make some changes to the data to see if it's always going to be the case that validation and training track each other, or if you can expand that gap in your own experiments, starting with my code if you wish. So for the small neural network, we have high training and validation mean squared error, at least relative to the large neural network. It seems to be underfitting a little bit. It seems to be relatively underfitting, which is why this relative is here. But the trend seems to be still downwards, even though the curve that the smaller neural network learns seems to be a bit simplistic. It's not too far off of what we'd like, so I'll leave that there. I'm saying it's too limited to capture the pair of sinusoids well, but that's as maybe. That's for you to think about, and come back if you have any comments. Here's our second worked example. So we're going to do classification now, going from regression to classification as we often do, and talk about the generalization gap a bit more explicitly. So now we're going to do, again, 2 neural network classifiers with different capacities. We're going to use scikit-learn's digits data set, and then we're going to compare similar kind of metrics like we have been repeatedly. So we're going to load the digits. This is about 1,800 8x8 images. And then we're going to just, again, have training and test splits and do the same kind of thing, but try to look at the generalization gap as an outcome. Here we're just loading the data. Here we're training the data simply. So here everything is, here's going back to scikit-learn. So making a neural network, we'll have our favorite pipeline. We'll do standard scaling. We'll have a number of hidden layers, which are passed in as a parameter. ReLU is our activation function, et cetera, et cetera. And we'll make 3 of them. A small one with 1 hidden layer with 32 units in it, a medium one with 1 hidden layer with 128 units in it, and then a large-ish one with 2 hidden layers, each with 512 units in them. And then we will do some training and do some predictions, and then report on the results. And here are the results. We are getting 100% training on each of these neural networks on the training data. The validation accuracy fluctuates a little bit. It starts at 96 point. It doesn't fluctuate. It increases. The small neural network has 96.3% validation accuracy. The medium one has 97.2% validation accuracy, and the large neural network has 97.6% validation accuracy. And zooming in a little bit, the validation accuracy, so the gap in accuracy between validation and training is decreasing as we get bigger and bigger neural networks. Food for thought, is this the same behavior we saw a moment ago with regression? If so, why? If not, why not? So here, let's see. This is redundant. I'm going to remove this slide afterwards, pardon me, because I put this in the previous one. Yeah. I wanted to look into the, again, like looking at a table of results is one thing. Looking at the model and trying to understand what it's learning is an important step in all machine learning. Again, it's insufficient just to put up the first set of results we have and then walk away. We want to dig in a little bit and just to make sure that no weird, unexpected behavior is occurring. This is our best model, and this is, again, the digits recognition. So we can look at a confusion matrix where we have our 10 digits and we have the number of times we have, predicted classes for the true labels, and we can compare the total number of times these co-occur. And as we'd hoped, the confusion matrix has, and as we expect given the accuracies we saw a moment ago, most of the activities on these diagonals, zeros are mostly recognized as zeros, ones are mostly recognized as ones, twos mostly recognized as twos, and so on. It might not be turning up so much in the video, but if you look at the slides, you'll see some slight light coloration around here with eights being sometimes recognized as ones, and I want to say nines being sometimes recognized as fives. At least there's somewhat lighter patches there, which is a bit of a surprise. You kind of expect sixes and zeros to be misrecognized as each other. Maybe there's a slight patch of lightness over here where my mouse is, but that's also as maybe. Nothing more to say about that really. But again, take the code, try to break it, and see what happens. So in summary, for deep neural networks, it's always important to do the sanity checks. Look at what the model is actually learning, look at the confusion matrices, make sure nothing weird is happening. Luckily or unluckily, in both of our examples, things behave kind of as we'd expect. Part of me kind of wanted to go in and break things out a little bit so the deeper and deeper neural networks would suddenly start behaving weirdly, just for the sake of the story of this course, to emphasize the message that deep neural networks aren't just magically better and you still have to be careful. That's the most important message I wanted to convey, to you budding machine learning experts. But it's also true that deep learning, this works really well, and it's also true that a lot of the time, as you increase the capacity, you'll just get better performance. You have to balance these two things in your head at once, always. In our examples, does training loss go down? Does validation loss flatten? Does it ever start increasing, like we saw in classical machine learning? The difference between validation accuracy and loss, which we implied was something to consider in previous modules. You'll look at that, do some experiments, and try to see if you can make these gaps shrink or expand. And think always why you're doing this. Why do you want the gap between training and validation accuracy or loss? Why would you want it to be as small as possible and be stably small? Try to do a couple of, again, I mentioned this before also, but it bears repeating. Try different seeds, try different hyperparameters to see if you always get the same behavior or if there's some kind of sensitivity to any of these manually provided numbers. And yeah, again, the same old empirical safety issues are important. If there are challenges, then you can always make sure that you have the validation and training data are really split. Again, we talked about that a lot in the past. You can vary capacity, you can vary the strength of regularization. Remember, we had these hyperparameters for how much regularization you're actually doing. Actually, dropout is something, I should have made a link to the very next module, which you'll see in a moment is going to be the topic, or one of the topics in the next module. Dropout is basically a form of regularization. Fiddle around with training time, when do you actually stop training? we provided these numbers, like do 200 epochs, but why is it 200? Can you stop training if you encounter some behavior in the training dynamics? Consider that and experiment with it. And then just, and for all these experiments, look at the generalization gap specifically and see how test performance, how it responds to your changes. So again, we've seen this classic view before. As a model capacity increases, the test error or the validation error typically has a sort of U-shaped curve, which we wanted to avoid, and we wanted to kind of fall into this sweet spot. But again, this is the last point. This is actually a part of a side-ish note, which is why we have these microscopes here. This is the idea of double descent, which is an old concept, but it's been in the news recently. It's been in the public discussion, so I think it bears mentioning here. In deep learning, for many modern models, we see this behavior called a double descent. So in the under-parameterized regime, test error will decrease with capacity, as we've kind of seen before, and we've seen like in classic models, and we've seen even in the neural networks we've seen in today's module. At some interpolation threshold, when you just have enough capacity to fit the training data, then test error will spike, which is similar to what we saw here. Like this behavior exists even in the biggest neural networks as you increase the capacity and you keep on training epoch after epoch. But in an over-parameterized regime where you have like a ridiculously huge model for some definition of ridiculous, test error will go up, but then it'll drop again. And these papers sort of define or describe this phenomenon, several years ago. The intuition is that huge models plus some careful optimization plus regularization plus a lot of data can at some point settle on solutions that are simple enough to get good performance. But at some point, they will retain that good enough solution, but keep on exploring for other solutions that might generalize well, and then get over this sort of hump, or a speed bump, I guess you could call it, and then they fall into a new regime which is even better than the first one that we encountered when we tried to find this sweet spot before test error started driving up. So here's a cartoon visualization from Belkin et al., which is from up here. Normally we have, this is the exact same, a cartoon I generated a moment ago. Overfitting is where you have very low training risk and the test risk goes up. But in a super over-parameterized model, where you have like way more parameters than you need, you will have the same behavior, but at a certain point when you get a bigger and bigger model, you'll eventually start decreasing your risk again afterwards, after you've gone over this speed bump, this little spike. And then you'll get to a point where your risk is even lower than it would have been in the so-called sweet spot if you had stopped training after too few epochs, for example. So this is the double descent. This is the first descent. There's a rise here because, oh no, you're overfitting, but then you have you're not actually overfitting in the grand scheme of things. You have this second descent, this double descent occurring at the back over here. This is actual, this is empirical data from this other paper I linked to. We have a small model where the dynamics is just like one descent over time. We have a intermediate model, which, you have too much capacity. Oh no, you're starting to overfit. This is the kind of behavior we talked about before. You're getting better and better, but then suddenly your test error, this could also be validation error, kind of goes up again, and then in this case, it stabilizes there. So this is the situation we wanted to warn you about. This is where we're talking about overfitting, and so you have to regularize and you have to make the models capacity, where capacity again is a bunch of factors, parameters plus regularization plus optimization, etc. Make the model a little bit simpler to avoid this problem. But it turns out that actually just having a supermassive model results in this empirical performance. We have our expected drop in test error. We have our spike, which looks like overfitting. But wait a second, if we just wait a little bit longer and keep on training, we overcome that error and we get the best of all possible models. Anyway, so this is an empirical realization of the theoretical viewed one here, and this seems to be the case for a lot of models that are super over-parameterized. I mean, super over-parameterized models require a lot of capacity, and sometimes this can be so much capacity that goes beyond those GPUs that I was talking about a little while ago, in particular the non-NVIDIA ones. But this is a phenomenon that is real and it's worth knowing about. So, the takeaway now, again, this is a bit of the complexity that I was warning you about at the beginning of this module. A simple rule, like we started having in some of the earlier modules, like more parameters means you're going to have problems generalizing. This isn't always going to be the case. At the same time, you have to balance that with the idea that bigger isn't always automatically better. Often when we talk about the scaling hypothesis and we say, oh, I'll just have more parameters, just have more data and you'll be fine, that is a very naive and simplistic way of viewing these models. So again, the levers we can pull remain the same. We can have our overall architecture, we can add more layers, we can remove layers, we can make the layers wider or thinner. We can add bottlenecks and skip connections, again, which is the topic of a future module. We have regularization at our disposal, including dropout, which we'll talk about next time, and data augmentation, which we talked about recently. We talked about different ways of doing optimization, adding data, augmenting data, doing data reduction potentially. We have an increasing number of tools we have at our disposal. These are all training tricks. I think training tricks is actually part of the title of the very next module. We have to be careful though, not to just kind of apply them randomly. It's going to be important to just realize when to apply them, how these tricks can sometimes play against each other and so on. But the name of the game here has been about validation. Increasingly, given this module, it's going to be about the difference between the validation and the training curves. I'm not going to go too much into risks and ethics every single time because it's getting a little bit redundant in some of these current modules, but just it bears repeating again. Big neural networks can memorize subtle but irrelevant signals. So hospital identifications, artifacts. This is similar to overfitting. It can learn, again, we saw previously where a neural network can learn like weird phenomena, like if there's a ruler in an image, there's a higher probability that this skin lesion is cancerous. This is something that big networks are more capable of doing than small networks. This could mean that it generalized poorly to new sites and new populations. So despite things like the double descent and like all these great results we're observing with bigger and bigger neural networks, go back to our original theoretical example, you still can have very good validation accuracy, but if you actually deploy it to an actually new site on actually new data, then things don't always generalize as well as they do in your lab. So memorization also obviously has an effect on privacy. These models are effectively kind of zip mechanisms or a tool for compression. So the bigger models mean you have to compress less, and if you have to compress less, then it's more likely that your model is actually just going to be a store of the data you use to train the model, in addition to all the patterns that it has learned. So be wary of that. And interpretability, again, we'll see soon enough examples where big neural networks have a good amount of interpretability. This layer is learning X, this layer is learning Y, and we're satisfied, but the bigger neural networks get increasingly beyond human comprehension. So just be wary of that as well. Here's just a few other links for you to follow in on how some of the topics from today touch on other topics. And as mentioned, large language models, because they're so interesting. You have many, many orders of magnitude more than billions of parameters. But these massive models often generalize to new tasks. One of the most famous papers, which I'll try to link to a little bit later, is it this one? There's a paper that basically shows that even if a model is trained not to do machine translation between English and French, for example, these massive models can become state-of-the-art machine translation models just because they've acquired so much information about English and French that it learns connections between them without being told to. And also, if you have strong regularization from pre-training objectives and data diversity, this results in models that are indeed very performant. So in later modules, we're going to look at representations and transformers and data that isn't always entirely labeled like we've been seeing. But this is going to come back to the ideas we saw today. The big, deep neural networks can generalize well if they're trained and evaluated very carefully. Speaking of evaluation, here are your quick sanity checks just for you to do at home. Here are the references from today. Thanks as always. See you next time.